Well, thanks very much. I'd like to start by thanking Ken and the staff from the Development Office for putting this affair together. I'm really happy to be here. And in fact, I hear we have a record crowd here today for the breakfast lecture. So I was busily flattering myself when, on the way in, someone pulled me aside and she asked me, "Is it true?" And I said, "Well, this is great. We have such an engaged crowd that I'm going to get off to a good start here talking about climate and energy." I said, "What is true?" And she said, "Well, is it true that they have huevos rancheros on the breakfast buffet?" So that knocked me down a few pegs, which is always good. But all joking aside, I'm really glad to be here because first of all, I love what I do, but I also think that it's really important for me to talk to my colleagues in other departments as well as business folks and community leaders like yourselves about these issues, because I think, as I'll show you in the talk, the decisions we're going to be making over the next decade or so are really going to determine what kind of climate impacts we see and what the future holds for us. So to get started, let's see if this, I'm not going to spend much time, as Ken said, talking about climate science or the impacts that we might experience from climate change. To get the details on that, you'd probably be better off attending a breakfast talk by one of the colleagues that Ken mentioned, like Eric Regnault or Jim Randerson, Michael Prather. But I do think it's worth a slide at least to remind us what's at stake here. So we're on track right now for 4 degrees of warming of mean temperatures relative to the pre-industrial by the end of this century. And at that point, that means we'll be dealing with the highest temperatures on the planet in 30 million years, so well beyond what any hominid has ever experienced. At that time, you'd be talking about sea level rise on the order of 2 or 3 feet, maybe more. Extreme drought over maybe 40% of the inhabited land right now, and significant reductions in crop yields, in some places up to 80%. It's probably going to lead to hundreds of millions of human refugees as they move out of areas that are inundated or no longer good for habitation, which will have conflict implications, more wars. Widespread extinctions, biologists think that it's plausible that half of known species could be extinct under that level of climate warming. And more extreme weather events, both in terms of intensity and frequency. So these are all some scary things. This is why we care about how we can solve the problem. Unfortunately, global CO2 emissions are rising. So this is a plot showing you annual emissions from the burning of fossil fuels since 1960. And you can see the trend here is basically up, with a few dips that you may or may not be able to read that correspond to global economic crises mostly. You might also be able to see on here that in the last decade, there's actually been a steepening of that curve. It's tipped upward. And there's been an acceleration of CO2 emissions as places like China have really rapidly developed and caused a lot of new emissions. And that's bad, because what the IPCC and the scientific community has told us is that warming, the amount of warming that we'll experience, is proportional to cumulative CO2 emissions. And so this plot is showing you on the vertical axis the amount of warming, they say temperature anomaly. And on the x-axis is the total CO2 that's emitted since the pre-industrial era. And you can see the shape of the lines on there are basically, like I said, lines trending up in a positive direction. So this is the case because CO2 has an effective lifetime in the atmosphere that's very long. In fact, if you drove here this morning, about a quarter of the CO2 that came out of your tailpipe will still be in the atmosphere in 10,000 years. So because of that kind of inertia, we have this function of cumulative CO2 driving temperatures, and it means that every molecule of CO2 that we put out is essentially just a tiny nudge on the global thermostat. We're nudging it up, and it's an increment of warming. And the reason, of course, that this is bad is underneath here on the same axis I'm showing you the amount of known resources of fossil fuels. And these are conventional resources, mind you. We're only scratching the surface of what some of the unconventional types of fossil fuels are. But you can see on here that the total proven fossil reserves, is the bottom gray line, is off the end of the chart. So that means we're going to be in the range of 5 or more degrees of warming probably if we burned all the known fossil fuel supplies. So I like to use the analogy of a cookie jar. We have these fossil fuels, they're valuable, they're useful, they're in the ground, It's like a cookie jar that we have to walk past for the rest of human civilization and leave them in the ground, not burn them and put that CO2 in the atmosphere. So what options do we have? And some of you may have seen this. I like to present the options on this vicious cycle. And it starts at the top. In case you can't read it, it's a little bit small. I'll read these to you. Starting at 12 o'clock, we have a desire for improved well-being. And I think that no matter who you are or where you are in the world, you're desiring to make your situation better. Whether that's buying a brand new Mercedes or it's getting light for your house at night. But nonetheless, that desire for improved well-being often translates into a demand for goods and services. So that's where we're moving clockwise around this cycle. The demand for goods and services then in turn drives a demand for energy, and in particular the cheap energy and easy energy that comes from fossil fuels, which is why the energy demand leads to CO2 emissions. The CO2 builds up in the atmosphere and it has a negative impact on our climate and oceans. And that causes a reduction in well-being, and then that feeds back into this vicious cycle where we're wishing we had it better. And the reason I like to lay it out like this is that depending on where you break this cycle, you have a different option for contending with the problem of climate change. So I've highlighted those on here, but if you break the cycle at the point of desire for well-being not leading to a desire for goods and services, that's being conservative. You're conserving the goods and services themselves. So examples of this might be taking a staycation rather than traveling, or putting on a sweater like Jimmy Carter instead of turning up the thermostat. These are conservation methods. If in turn you don't conserve, but you have the demand for goods and services and it doesn't use as much energy, then you're being efficient. And so this is getting A to B in a Prius instead of a Hummer or something. So you're still getting the service, but you're not using as much energy to do it. If you demand the energy, but you don't produce CO2 emissions, this is the whole suite of technologies which I'll be talking more about today that are carbon-free. And that's using the term loosely. There's some that entail little bits of emissions here or there, but they're not burning fossil fuels is the point. If the CO2 emissions are produced because you burned a fossil fuel, it may be possible, there's a suite of technologies for this, to capture those and store them away somewhere out of the atmosphere, and those are called carbon capture and storage technologies. If the CO2 does make its way into the atmosphere, but you don't want those negative impacts on the climate system or the oceans, there are some things available that we're at least researching called geoengineering approaches, and I'll mention those later as well. And finally, if the negative impacts do materialize, there may be ways to adapt to those things, cope with them, and so not experience such a reduction in our well-being. And the last arrow on here that I didn't label, you might call suffering. Right? So these kind of fall out into three broad areas. The mitigation side, you'll hear people use this fancy word, mitigation. That's really just talking about avoiding the CO2 emissions to begin with. Intervention approaches are kind of these geoengineering ideas of how can we manipulate the climate intentionally to offset what we're doing with our CO2 emissions. And then adaptation and suffering are the last part. So what I want to start by saying is that it's really important to know that it is still possible to turn this ship of climate change. A lot of people think, well, climate change is happening, it's run away, there's not much we can do about it, we better start adapting. That's not exactly true. There's a lot of inertia in the system, but it's theoretically possible to turn the ship. So what I'm showing you here is a plot of CO2 emissions over time into the future under the hypothetical case where we never build another power plant or vehicle or anything that burns fossil fuels. So all the existing fossil fuel burning devices stick around and they extend and live out their expected lifetime, but we never build any new ones. Then you end up with this kind of tapering curve of emissions as all of these devices age out and are retired. And the grand sum of CO2 emissions here amounts to about 500 billion tons of CO2, which is more or less 15 years of emissions at current rates. If we were able to do that, though, I fed this into a climate model. This is some research I did a couple years ago. And you could see that the climate system, the temperature change relative to the pre-industrial era, stabilizes itself by 2060 at around 1.5 degrees. far less than the 4-degree futures that I was talking about with all of those really grave impacts earlier on. So I think in theory, this is really great news. It means that if we started today building the right things and stopped building the wrong things, we could avoid these kinds of climate impacts. The problem, of course, is that we're not doing that. This is the same plot of emissions going in the future, but here, the first plot I had shown you, I didn't mention this, it was the different sectors that those emissions come from, mostly energy and cars. Here I'm breaking out the same emissions by where these emissions are expected to happen if we stopped building things today. And I think the interesting features are those purple wedges at the bottom that are relatively flat on top. Those are China and India. And so these are places where the infrastructure tends to be young, and we can expect a lot of emissions in the next couple decades from those places because of that young infrastructure. In contrast, the US, which is the paler blue, and Europe and Japan, which are the green and yellow, you can see those things taper off very quickly in the next decade. So I think this is an important point because it says that what we're doing now in the next decade is really critical. If we allow these things to age out and we replace them with carbon-free alternatives, then we're on the road to success in terms of combating climate change. If, on the other hand, we double down on our fossil fuel infrastructure and we build a whole other generation of coal plants or gas plants, then we could be in for a much more extended version of this curve, and that's how you end up at 4 degrees. And unfortunately, that's exactly sort of where we're going, the negative side of things. To use that ship analogy, turning the ship, we're still proceeding full speed ahead. So this is some work that I'm doing now as a follow-up on that. And what I'm showing you, it's a little complicated, but the idea here is when you build a power plant, you could expect that power plant to stick around for 40 or 50 years and emit CO2 over the entire period. Normally, we account for the CO2 in the year that it gets emitted out of the smokestack. This is an alternative view that I'm working on where you would instead allocate the expected lifetime of emissions in the first year that that power plant is built. And so this really is the idea that it would help a decision maker to understand the long-term implications of what we're doing today, the investment decisions that are being made today. So this is a plot showing you for power plants around the world since 1950, how much we've built and committed ourselves to in each year. So the top part, the light green part, you can see that in the 50s and 60s, maybe we were building enough power plants to commit ourselves to a few billion tons of carbon emissions in each of those years. And the black part underneath is actually showing you that most of those have now been realized. Those commitments are realized. In other words, they've happened. In the 70s and 80s, there's a step change, and you see that all of a sudden the commitments to future emissions jump up to around 10 billion tons a year. And those in the 80s, you can see below that it's not all black anymore. There's some dark green there, and that's telling you those things are still outstanding. There's still some debt to be paid on those commitments. And unfortunately, towards the end of the plot in the 90s and the aughts, you can see that we have another jump up. And we're building so much stuff that we're in each year committing ourselves to 15, 20 billion tons of CO2 emissions. For comparison, that blue line is the actual annual emissions from power plants around the world. So the point here is that we're building and committing ourselves in the future to more than we're actually emitting. And so the balance owed is growing, and the commitment to climate change is therefore growing. So all of this begs the question, why aren't we stopping? And I think this is a fascinating and critical question to answer, and it's one that our grandchildren will probably ask us in an accusing way. But why can't we stop ourselves? So at the risk of provoking my physical science colleagues in the room, I think I want to make the point pretty strongly that the problem is not a lack of science. Saying that we're not doing something about the problem of climate change because we don't have good enough science is like saying I eat bacon for every meal because my cardiologist can't tell me what day I'm going to have a heart attack. It's like saying Poland didn't know they had a problem because they didn't know the thread count on the Nazis' uniforms, right? And in this way, I think this is an important point because this is a different kind of problem than, say, the one Sherry Rowland had to deal with here. where the biggest challenge was just proving that CFCs were having an impact on stratospheric ozone layers. And once that was done, it seemed like it was a relatively quick process to then transition and do something about it. We know we have a problem with climate change. We may not know exactly how big it's going to be and who it's going to flood and who's going to be damaged, but we know plenty that we should be getting going on this. So again, why aren't we stopping? Do we have a psychological problem? And I'm only half joking with that. There's actually some interesting science behind this. A lot of what I'm going to say in the next few slides is cribbed from a Harvard psychologist by the name of Daniel Gilbert, some of you may know. But he comes from the background of evolutionary psychology, and he makes a strong case that the threat of climate change doesn't have certain features that threats that we tend to respond to do. So let me give you some examples. We are, as humans, uniquely able to plan for the long term. And that's why we're able to floss our teeth to prevent gum disease, and we invest to secure our retirements, and we exercise and eat well to stay healthy. But, you know, living with a wind turbine on the horizon of your beach home, maybe not, right? Why is this such a problem for us? So coming from that angle of evolutionary psychology, the first thing that Daniel Gilbert points out is that climate change is not intentional. And so he makes a case that humans are obsessed with human agency. The slightest whiff of a human intent gets our attention and gets our imaginations going in the way that the biggest accidents don't. And so that's why, for instance, people see faces in tortillas, but none of you have ever mistaken anyone's face for a tortilla, right? It's also the reason that things like 9/11, everyone the world over can tell you what day that happened. But I submit to you that if a plane had flown into the World Trade Center by accident, many of you in the room might not be able to tell me what year it even happened in. Similarly, we had people taping up their doors and wearing gas masks outside the house because anthrax spores were being mailed around. But you can't muster the energy to get a flu shot some years, and yet the average death toll of anthrax in a given year is exactly 0, and the average death toll of influenza is 36,000 a year. So climate change is not intentional. I think it's fair to say if climate change were driven by evil bearded men on the other side of the world, we'd all be massing in the streets. We'd be fighting a war on climate, but we're not. The next thing climate change isn't is it's not disgusting. There's certain threats that we have evolved a visceral response to. They make us nauseous, often to do with health. And that's why there's rules around the world about what and when you can eat, how you can touch other people, but there's very few rules about when you can run your air conditioner. It's just not something that grabs us in that way, so it lacks that feature as well. It's also, this is important, it's not immediate. So our brains are elaborate get-out-of-the-way machines in some ways. So if I threw a baseball or if this tiger walked in the back door, you guys would scatter out of this room before you even really realized what was going on. Climate change doesn't have that feature. It's not nearly as immediate. It's a long-term threat. It's something that's going to ruin your future, but it's not going to ruin your evening, right? And so that's a problem in terms of motivating human action to deal with it. And the last feature that the evolutionary psychologists talk about is that climate change isn't fast. And this is counterintuitive to a lot of the biologists or even physical scientists in the room who think that climate change is happening so fast that these natural ecosystems and human systems in many cases can't keep up. But it's actually unfortunate with regard to the fact that you can't observe the changes on a daily basis. It's something that happens over generations. It's the proverbial frog in a slowly warming pot of water. And we're not seeing the changes in a drastic enough way to really spur our action. So we know we have these host of psychological biases, issues around the climate issue. But I think those are actually only part of the explanation. And I think the bigger problem is that fossil fuels are pretty great, like those cookies in the cookie jar. So to start, I think it's important to understand, in case you don't, that we get about 83% of our energy, at least in 2012, from fossil fuels. They are the way that we make energy. We do have some renewables. The renewables line in green on this plot is mostly hydro, so don't think that that's solar and wind. Those are a very, very small portion of that. Nuclear is another one, but it's a laggard compared to the fossil fuel dominance. So I'm going to tell you 6 ways that fossil fuels are great, and the corollaries to all of these are reasons that we should be worried about how to ramp up renewables and low carbon alternatives. So the number 1 reason, I think, is that we have a lot of fossil fuels. And not only that, we've spent 200 years and tens of trillions of dollars developing the largest network of infrastructure on the planet to support those fossil fuels. So, not only do we have those big deposits that I mentioned earlier of coal and gas, but we have filling stations and substations and transmission lines, and we have pipelines and specialized equipment for mining these things. A lot of these things have a lot of value in a world where we're burning fossil fuels, but maybe not so much in a world where we're getting a lot of our energy from wind or solar. So that's a thing that's great about fossil fuels. We have a lot of them. The second way that they're great is that they're on demand. And I chose on demand rather than some more engineering speak because I'm sure a lot of you like your HBO and that might resonate with you. But on demand power. So this is a plot just showing a daily power demand, just an average demand. You can see it's sort of low and during the middle of the morning, and it rises around this time of day. And then by the end of the afternoon, as everyone goes home from work and turns on their TVs and their ovens, then it peaks in the evening time and drops off again as people go to bed. The beauty of fossil fuels is if you see a spike, whether it's a large curve like that or even a very sudden demand, it's very easy to respond to that. You just press the accelerator down and you're off to the races. As long as you have the fossil fuels there, you're good to go. Fossil fuels also have a very high energy density. And this is something maybe a lot of you haven't thought a lot about, but it's the reason that you might prefer, if you're a backpacker in the High Sierra, to carry a granola bar instead of carrots. The same weight, you get more energy. So you could also talk about energy density in terms of volume, but I think for this, I wanted to focus on the weight. And so whether you're talking about food like that, and by the way, the units on here, joules per gram, which joules is a unit of energy. You could also see the trend in fuel sources. So dry wood has no more than 17 megajoules per kilogram. Coal, you're already up in the mid-20s. And refined oil products like gasoline, you're in the mid-40s. So this is why we don't have wood-powered cars. Lithium-ion batteries, less than 1 megajoule per kilogram. Just sort of a footnote there. If battery technologies aren't very great, not yet. They also have high power density. So by power density, what I'm talking about is the area of land that you have to dedicate to this energy source. If you have a coal-burning power plant, even if you consider in addition the area of the mine that you're getting the coal from, you can generate 1,000 watts for every meter square of ground. In contrast, to do wind, you need a lot more area. You only get 2 watts for a meter square of wind on average. And solar's a bit better. You might get up to 20 watts per meter with some of the more efficient panels that are on the market today. So the fossil fuels have a big advantage here because we don't need to take up vast areas of our landscapes to use them. Number 5 is that they're safer, right? At least, disasters like Fukushima put us all sort of in a somber mood and say, well, isn't it great that we have fossil fuels? We can all breathe a big sigh of relief, right? Of course, unless you're in China, where breathing is a liability. And so, I think this plot on here is showing you that, in fact, maybe this is the question mark after safer. Maybe it's not so clear that they're safer. There's a lot of research out there that indicates that nuclear, for instance, has far lower death tolls and far lower CO2 emissions than some of the alternatives, including natural gas. And the final way, and the most important by far, I would say, is that they're cheaper. Fossil fuels are cheaper than the alternatives. So what I'm showing here is a bar chart of the cost of building a new power plant in 2011, broken down by different fuel types, different technologies. And you can see the lowest cost on here in those years when gas was even lower than it is now, were gas-burning power plants of combined cycle variety. And then you have things like wind, geothermal, and hydro, and then some more fossil fuels. But I think what's important to note on here is that some of these things like wind, geothermal, and hydro have their own issues, and I'll go through those in a bit more detail. But suffice it to say, if you want to build a power plant and you want to spend the least money to do it, you're going to build a fossil fuel burning power plant today. Why though? Well, there's a couple reasons why. We have a lot of these things and they are cheap. We have that supporting infrastructure, but there's also a lot of direct subsidies of fossil fuels. So this is a comic with a guy with a huge big oil profit belt, and he's got his suspenders that say tax subsidies, and he doesn't want to lose the suspenders. So there's on the order of $500 billion a year that's actually been calculated by the International Monetary Fund going to fossil fuel industries. And so that's a little extra advantage on top of the ice cream. But the real reason that they're cheaper, I would submit, is that they're not incorporating the cost of a lot of the pollution that's coming out from them, whether it's air pollution or CO2 emissions. They're not bearing any of the cost for the CO2. And so that's essentially a huge subsidy to fossil fuels because they're not having to pay the cost of the damage that they're doing. So then coming back to the circle, we now know pretty well we've got some psychological problems, but if we can get past those and figure out how to take action on this, how do we combat all of those advantages to fossil fuels? How can we address this problem using all of these approaches with the least cost and the least risk? So I'm going to walk through some of the different options we have. So starting out with the conservation and efficiency angles. And I think it's pretty clear that if you can conserve energy or you can be efficient, you're saving money. So it's affordable by definition. When people can be convinced to do this, I think we absolutely should do it, and we need all the help we can get in terms of reducing our energy demand. And that's because there's two other things that I think are important here. You'll never get to zero fossil fuel emissions, which is what you need to do if you want to truly stabilize the climate with conservation and efficiency alone. And you can only be so efficient, and so if you're using fossil fuels, you're still going to have some CO2 emissions. The second thing is, it's one thing to convince an American to drive a Tesla or double pane their windows in their ski house, but it's quite another to tell someone who doesn't have any energy services, as maybe 3 billion people on the planet don't, that they can't use some more energy. I think it's highly desirable that they actually do get access to those energy services, and that's what human development, things like the Millennium Development Goals are all about. So I think conservation and efficiency is something we should absolutely pursue. It's going to make the job easier, but it can't solve the problem on its own. And we should expect that energy demand globally is going to grow. It's actually expected to double by the mid part of this century, 2050, from where we are now. So that leaves us with this decarbonizing the energy system as our next alternative. What can we do in the way of these different technologies? So I mentioned solar earlier. It's a very large resource and it's getting remarkably cheap. The prices of solar photovoltaic panels have dropped tremendously even in the last decade as China has started manufacturing them in a big way. And wind is something that's now a fairly mature technology. It's a sizable resource depending on where you are around the world, but the economics are already competitive. So these are encouraging things. The problems with those, and this gets back to all those advantages of fossil fuels I told you, is that both of these share a similar set of problems. The first being they have low power density. So I told you that they need a large area. So you need something like 500 acres of wind to replace 1 acre of a coal plant. And that's a lot of resource, especially because we're talking about wind in an area that's pretty good for wind, not just any area. The same goes for solar, although slightly less, maybe 50 acres for a really good solar concentrating facility. But the problem with that large footprint is that they also require lots of new infrastructure to build power lines to connect these things together and to bring the power from the places that are windy and sunny to the places where people need energy, which are all too often not in the same place. But the most concerning problem with things like wind and solar are that they don't have this on-demand HBO feature. So the lower left here, what I'm showing you is a plot, and don't even try to read the axes, I apologize. The horizontal axis is a time over the course of one day, and the vertical axis is energy. And the pink line is showing you the average demand for energy in California during the summertime, while the black arch there is the output from a solar cell. So I think you can see the problem pretty quickly that while in the middle of the day around noon we might do a great job of meeting demand with solar, there's a lot of the day we're not going to be able to meet that demand with solar energy. And that's really being a little bit generous, because the real curve of solar looks more like this, where clouds are passing and there's sudden dips in the solar demand moment to moment. So there are ways that we can tackle this, and I'll talk about them in a second. But that's a challenge, and it adds cost to solar. And the lower right is a similar plot, but for wind. And in this one, the dark blue line is showing you the wind energy that's been produced over a course of several days in Denmark. And the red line is the demand for wind. And so while you could see that those two lines intersect them in a couple of places there, meaning that the wind could have done a pretty good job of meeting all the demand, in other places the wind is nowhere to be found and demand still keeps cranking along. So this is a problem. And I mentioned there are ways to get around it. One of the main ways that people talk about surmounting this problem is, well, we can build a lot of these things and we can spread them out over large distances. The assumption being, well, if a cloud passes here, it won't be passing everywhere. We have a solar panel at the same time. Or if the wind dies here, it won't die in Minnesota or somewhere else that's connected. And I think that's a valuable approach, although it assumes that you have money to burn, because it's essentially saying it's okay if my wind turbine only operates 25% of the time, I'll build 4 of them. It's kind of like saying if you had a car that only started 1 in every 4 days, the answer would be, well, buy 4 or 5 cars. You'd be good to go. So I think it's a solution, no question, but it's going to cost us, and so that's an extra cost. There's also the idea that people have of batteries, and I think, and I mentioned it earlier, the battery technologies that we have right now aren't up to the job of doing a utility scale storage of wind, at least not at a big scale, like a community scale. So that's an important area of further research, to figure out what can we do with batteries. There's other things besides chemical batteries, like compressing air underground or pumping water up the hill and letting it back down when the sun sets. And those are promising things, but they're also concerning because of this power density issue. We'll then have to start covering areas with big reservoirs or finding caverns to pump air down into. A really promising technology in the area of solar, though, for surmounting this intermittency or not on-demand problem is solar thermal, that concentrates the heat from the incoming sun into a central conduit, which you might be able to make out in the upper right there, those red lines. And those conduits are filled with molten salt, which has a very high heat capacity, and it gets hot enough that even after the sun sets, these things can generate power well into the night, depending on the size of the molten salt reservoir, maybe even all night. So unfortunately, if you can think back, and I'm sure you can't, to the plot of the cost of different energy technologies, this is the most expensive one on that plot that I showed you. So it's not cheap yet. We need to keep building these and learn how to do it cheaper. Nuclear, everyone's favorite, especially since the San Onofre closed down. I think nuclear is one that you can get into trouble depending on which audience you're talking to, but it's a sizable resource, and it is something that we know how to do. Depending on who you ask, it may or may not be economically competitive. You know, there's all sorts of government backstops and subsidies and things that go into that, but those of us that have been buying energy in Southern California from San Onofre for years know that it's at least affordable in theory. The problem, of course, with nuclear is not a technological one. It's that it's unacceptable to the public from a safety standpoint. And I think this actually tracks back to some of the discussion we had about those psychological underpinnings, and that we're afraid of big, immediate, catastrophic meltdown sort of incidents, even though the long run record indicates it's pretty good compared to some of the alternatives of fossil fuels. And so, yeah, I meant to bring that up. That's the Fukushima and Yucca Mountain, which got significant public opposition from Yucca Mountain, and Fukushima really closed down the nuclear industry in a lot of countries. There are prospects for doing nuclear better. The fuel cycle we're using today is the same one we started with in the mid-50s. And it's not that it's not safe, but it's burning up a lot of uranium, and it's a once-through fuel cycle. So there's an issue too that even if we wanted to do nuclear in a big way, we might run low on fuels. So other fuel cycles, things that are less proliferation prone, safer, people are working on these things, and that would use different fuel cycles that could recycle fuels or use some of our spent fuels from the existing facilities as fuels for the future. But as I said, I think it's up in the air whether these things are going to have much luck given this pretty tough public opposition that they face. Bioenergy. Bioenergy is great. I think it's something that makes a lot of sense if you're using, say, municipal solid waste to generate biofuels or something like that. I think it stops making a lot of sense when you start to use very large areas of otherwise good cropland to grow fuels. It has a very low power density, just as wind did. About 2 watts per meter squared is where you're at with biomass. And it's not necessarily carbon-free if you're tearing down something like a forest that takes 50 years to regenerate. There's a lag there. So I think the big problem with bioenergy is that it competes with other land uses like agriculture when you get to large scales. It could end up making a lot of sense, though, with things that we really need liquid fuels for, like aviation. Hydropower. So hydropower is great. It's affordable, and it has the characteristic of being on demand. You can open the floodgate and close it whenever you want. And assuming you don't have a protracted drought, you'll be good to go. The problem with hydropower is that you need 2 things for hydropower. You need water and you need elevation. In the US, the eastern US, we've got tons of water. The western US, we've got plenty of elevation, but not so much in the same place. So where we do have these things in the same place, the state of Washington, for instance, we're using a lot of hydropower. Washington generates something like 80% of their power this way. So it's a good idea. It has some issue with size. The size of these reservoirs gets pretty big, and that can be a problem from the standpoint of public opposition, whether it's an environmentalist thing or it's places in China where people are living in these valleys that are having to be displaced. But I think China is a good example, and that's what I'm showing here. This is the Three Gorges Dam of what you can accomplish when public opposition is not a factor. So natural gas. I haven't mentioned this. It's not a carbon-free energy technology. It is a fossil fuel. It may help us transition away from the lesser, it may be the lesser of 2 evils, transition away from things like coal that result in even more CO2 emissions for the same amount of energy. But it is only a transition, because if we want to get to 0 fossil fuel emissions, we have to get off of fossil fuels. So I often use the analogy, kind of like the cookie jar, of if you were going on a diet, you could do reduced fat Oreos. That's where we're at with natural gas. It's better than full fat Oreos, and that's what could be said about it. So some work that I'm doing on this topic in particular shows that without a climate policy in place, gas begins to compete with things like solar and wind. It's not just competing with coal. And so under that scenario, you can see here on the left is a scenario where there's a low supply of gas, and in 2050, renewables make up 37% of our energy. This is the US. On the right, we have a scenario where there's abundant gas, so therefore gas is cheap, and you can see in 2050, renewables are only 26% of our total energy. So it's great insofar as we have a climate policy that can steer the benefit of gas towards offsetting coal. It's not clear that it's so great when it's actually biting into the renewables. So that was the energy. This is the related plot of what CO2 emissions do under these low and green and high gas scenarios in red. And you can see that the no policy bars on the left side are pretty much the same height. Those little black bars are depending on your assumptions about leakage. In contrast, if you have a $25 a ton tax on carbon that ratchets up 5% a year, that's where you're at on the moderate policy here. Those bars in the middle, you see there's a huge dip in the total CO2 emissions. But again, not a whole lot of difference between the high gas and low gas scenario. So it's not clear that just having a lot of cheap gas around is going to help us reduce our CO2 emissions. So moving on from the carbon-free energy, I've covered the big ones. let's talk for a second about the idea of carbon capture and storage, which again is if you create the CO2 emissions by burning a fossil fuel, you want to capture them and store them somewhere out of the atmosphere. So we know this is technologically possible. This is an example of a facility in the North Sea that's operated by Norway that has been doing this for several years now. They actually pump natural gas out of the North Sea, and then they bring CO2 back and pump it down under the seafloor into a cavern there, and they're sequestering under the seafloor about 1 million tons of carbon a year. So we know it's possible. The problem, of course, with this kind of technology is that there's not really a market for it. As long as you can dump CO2 into the atmosphere for free, why would you pay to carry it out to the North Sea and pump it underground? So it really it seems like it's something that could scale up, and it could be a really nice way to reduce our CO2 emissions quickly, but it's going to cost us, and that's what this plot is showing. So here on the x-axis, the horizontal axis, is the CO2 emissions per unit of energy. And on the vertical axis is the cost of electricity. So you can see where the red and the yellow bubbles start out to the right has a lot of CO2. Installing this carbon capture and storage technology brings those CO2 emissions down by 80 or 90%. But at the same time, the resulting electricity is anywhere from 20 to 55% more expensive in this study. So again, this is something we could do, but it's going to cost us just like some of the other renewable technologies will. Which leaves us with some sort of last-ditch approaches, and I'm talking about geoengineering and adaptation to some extent. And so I like to lump these together, not because they're technologically similar, but because I think they suffer from the same problems. And that is they're either expensive, risky, or both. And so let's talk first about geoengineering. There's really two flavors of geoengineering. The first is much more innocuous. So they call it carbon dioxide removal because they're taking CO2 out of the air and putting it somewhere else. So things like planting trees, reforesting the Amazon is what you see in the upper right there as a carbon dioxide removal approach. There's also more industrial solutions like this thing in the bottom left that's someone has built amine scrubbers that actually absorb the ambient CO2 and where it can be pumped away and stored underground. The problem with these approaches is that they're expensive and difficult, and it has to do with the fact that they're undoing climate change the same way we did it, and that is molecule by molecule of CO2. So they're physically moving molecules of CO2. They demand large amounts of energy, large amounts of space, so that's all bad. But they have very low risks because they are undoing it just the way we did it. We know how to do this, and it's not going to be a big problem probably to plant some trees. That's very different potentially than the other flavor of geoengineering, which some of you may have heard about, called solar radiation management. It's essentially blocking sunlight from coming into the planet by putting reflective particles, often sulfate has been proposed, in the upper atmosphere. And one of the advantages to this, or perceived advantages, some of the researchers say, is that we know that it works. And the reason is we have these natural experiments where there's been very large volcanic eruptions that have put a lot of sulfate into the upper atmosphere, such as this picture of Mount Pinatubo erupting in 1991. And the bottom there is showing you the climate response from that Mount Pinatubo eruption in 91. And you might be able to make out in black is actually the observed temperature change. There was a decrease of about 0.5 degrees globally for a year or year and a half after that eruption. So we have evidence that this works. Unfortunately, it also has some side effects. For instance, that same response led to changing precipitation patterns. The lowest runoff in the Ganges River ever recorded happened during this period of time. So there's more than just the temperature that's being changed by this. It has advantages of being cheap and easy. And by cheap, I mean absurdly cheap. A single fire hose could carry enough sulfate to offset a doubling of global warming. So it's a big lever on our climate system. Unfortunately, it has really big risks. Although we know that it can work and we have these short-term natural experiments, we have no idea what this would look like over a long period of time, whether natural ecosystems would respond negatively to this sort of thing. We also have the problem that if we start blocking the sun to cool our planet, but yet we keep emitting CO2 in the meantime, then the difference between the temperature the planet wants to be at and the temperature we're keeping it at gets progressively larger. Which means if we ever have a lapse and we stop doing geoengineering for a minute, we're going to have such an outrageous ramp up of temperatures that we won't even know what hit us. So that's really a frightening thing. So there's some big risks associated with this. Finally, the idea of adaptation. And I think adaptation is, again, similar to geoengineering. There are flavors of adaptation that are no-brainers. Building new buildings further from low-lying areas, right? That seems like something we should definitely pursue. I think, on the other hand, if you're depending on a strategy of coming up with new crop types that are miraculously drought and heat tolerant, and you're moving agriculture wholesale from one area of the world to another area of the world, these things are going to be very expensive and potentially very risky. And importantly, even if we did manage to do those things in the human side of the system, it's not clear that natural systems are going to be able to respond in the same way. So things like ecosystem services provided by bees to pollinate our crops, or the water purification that we get from natural wetlands. If those ecosystems, the natural ecosystems, can't adapt in the same way that we're forcing our human systems to adapt, we may be out of luck anyway. So that sort of leaves us, I think, with the least cost and the least risk invested in these carbon-free energy approaches, where we're trying to reduce CO2 emissions and prevent the climate warming before they happen. I've shown you, we have some technical hurdles. There's a lot of problems with some of these renewable technologies, barriers to scale, both social, political, and scientific. But I think it's really incumbent on us, and hopefully I've convinced you that over the course of the talk, to pursue strategies, policies, and investments that accelerate the innovation of these carbon-free energy technologies, because they really do pose the least cost approach. So just a few take-home points. I told you that the climate impacts are here, that more are coming, and importantly that we know enough now that we know we need to do something. I said that human psychology may be contributing to this problem, and I think the important thing there is to recognize that, be cognizant of it, and respond accordingly. I told you about all the great features of fossil fuels, and I think that's important. It's sort of a know your enemy approach. You need to know what fossil fuels are good at, why they're dominant, in order to displace them. Conservation and efficiency, I think no-brainers a lot of the time. They're affordable, we should pursue them, but they're never going to completely solve the problem by themselves. Carbon capture and storage may be available at large scale, but they're going to cost us, just as some of the other energy technologies will. Some flavors of geoengineering and adaptation are straightforward, planting trees, not building in low-lying areas, those kinds of things. But there's a lot that are very risky or expensive or both. So again, coming down to it, I think the keys here are to support policies and investments that accelerate the development of carbon-free energy sources. And in particular, the ones that often get talked about are putting a price on carbon somewhere. This works to price that externality, price the pollution that those things are producing now and not paying for, and therefore makes all of the non-carbon emitting technologies immediately more competitive. On the other end of that, I think it's critical that, and especially in places like universities, we support innovation and research, development, and deployment, which is the other D in RD&D of these technologies, because the more we do, the more we invest in the research, and the more we actually go out and build in the world, the better we get at it, the cheaper the technologies get, and the more feasible solutions look. And that's really it. Thanks.